Done.
Okay guys, so today we are going to discuss something about the Kepler's laws of the planetary motion. Now, when you talk about the motion of the planets, you already know that the planets revolve around the sun, isn't it? There was a scientist by the name Kepler who for the first time tried to observe the motion of these planets around the sun. Okay? The name was Kepler. This guy for the first time tried to observe the motion of the planets around the sun. Okay? So, and he observed a lot of things, and then he came up with certain laws known as the Kepler's laws of the planetary motion. Now there are three laws, and on the basis of these three laws we can actually have an information about how the planets revolve and what is their orbit, what is their speed, okay, and what is the length of 1 year on each planet. We can also do that. Okay. Now, what are these laws? The first thing that I want to show here is, for example, this here is Sun. Okay, and we have a planet here which is trying to revolve around the Sun with speed v. Okay. Now, the first observation that Kepler made was given in the form of law of orbits. This is the first law of Kepler, law of orbits, as per which Kepler said, when the planets revolve around the sun, they revolve in an elliptical order. Which orbit? Yes? Elliptical. Okay? Most of us have drawn solar system in our previous grades, and we have always shown that by circles, right? But that reality is that it is not a circular path, it is an elliptical path. And an ellipse, for an ellipse you need to have an information. For an ellipse, remember, we have two foci. When you talk about a circle, for example, this is a circle, we have a center, isn't it? Right? But in case of an ellipse, we do not have one center, okay? We have two foci. See, if I draw the two axes here, let this be the x-axis and let this be the y-axis, okay? You are seeing that Sun is not at the center. This is the center, okay? Sun is not there. Sun is at a different point. Now this point here, it is called as the focus. This is the first focus, and then we have the other focus as well. But the other focus, which of this elliptical path, is unknown. It can be anything. It can be some other planet, it can be some other asteroid, it can be some other comet, that is unknown. So one of the foci is always fixed, and that foci is the Sun. Is that fine? So when the planets revolve around the Sun, it is not a circular orbit like this. It's not that Sun is at the center and the planet is going like this. No, it is not like that. It is going around the Sun in an elliptical path, and remember, for an ellipse we have two centers which are known as the foci. Okay, F1 and F2, F1 and F2 are the foci of this path. Okay, one of the centers, F1 for example, of the Sun, we know it. Okay, we know the location of the Sun, and the planet goes around the Sun. Okay. Now the path of the planets is elliptical, and you must remember the equation of an ellipse. The equation of an ellipse is x squared upon a squared plus y squared upon b squared is equal to 1. This is the general equation of an ellipse. Any path which is an elliptical path satisfies this equation. Is that fine? What is A and B here? See, A is the intercept on the x-axis and B is the intercept on the y-axis. Do you understand? Yes? A is the intercept on the x-axis and B is the intercept on the y-axis. And you need to understand one thing. A and B are not equal. One is bigger than the other. Sometimes A is bigger, sometimes B is bigger. It depends on what kind of ellipse are you drawing. Fine. If the ellipse is like this, in the one that I have shown here, A is bigger than B, therefore I will say this axis A can be called as the semi-major axis, okay, because it is the bigger axis and A is the half of it, so we can call it as semi-major, okay. But B, it being the part of the smaller axis, I can say this is the semi-minor axis. Is that clear? Okay. Is this fine? This is all the information that you need to know about the ellipse. Very important. The planet revolves around the sun in an elliptical path. So if someone asks you what is an ellipse, you must say that for an ellipse actually we have two foci, okay, and the path is symmetric about the x and the y axis, okay. The equation of the elliptical path is this: x squared upon a squared plus y squared upon b squared is equal to 1, where a and b are the intercepts on the x and b is the intercept on the y, okay. Now this a and b are never equal. If they are equal, understand, if a and b are equal, it will form a circle, isn't it? If a and b are equal, so this is a and this is b, if they are equal, they will be equal and it will form what? A circle. But this is not a circular path. We are talking about the reality. The reality is this is not a circular path. This is an elliptical path and we are not equal. One is bigger than the other. Therefore, one is semi-minor and the other one is semi-major axis. Is that fine? Is it clear? Now, when you see the planet revolving around the sun, very important. Should I take a picture of this because I want to show you the simulation now.
Is it symmetrical across its axis?
Yeah, the ellipse is symmetrical about x as well as y. It's symmetrical about both because, for example, you want to cut it through x-axis. So whatever is up, same is down, right? Similarly, if you want to bisect it with the help of the y-axis, whatever is here is also here, right? So it is symmetric on the both axes. Is that fine? That is why you see the equation, see? If you remember, I showed you the equations of parabola one day in the class. I told you the power is on x, so the graph will be symmetric about y. The power is on y, the graph will be symmetric about x. Remember? Here, the power is on both. Therefore, the graph is symmetric about both axes. Is that fine? Okay? Yes, take a picture and I will show you the simulation. The first law that we are talking about is the law of the orbits, okay? And now see what is happening. Should I erase all of it? Okay. Now see, this is the planet, this is the sun, okay? I cannot name it now. So you need to know that these crosses here are the two foci, okay? This A is the semi-major axis, okay? And this is the planet which is revolving around this sun in an elliptical order. Now see what is happening. See. See, observe, very important thing. At one time during its motion, your planet is very close to sun, isn't it? And at one time here, it is the farthest, isn't it? So these are the points called as, yes? Any idea about these 2 points? No? So these points are called as the epigee and the perigee, or aphelion or perihelion. Okay? How? I'll just name them. Just wait, let it work. See. The planet is going around the sun. At one point here, it is the farthest, and when it is going like going, here it is the closest, isn't it? And one more thing that you're observing, very important thing that you're observing is, what is the speed here? 34.48, right? See what is happening to the speed. Slowing down Only 17.24. So what does that mean? When the planet is the farthest, it has the least speed, isn't it? And when the planet is very close to sun, what happens? Its speed increases. So the speed of the planet around the sun is not constant as well. Very important thing. Why is that happening? I will show it in the second law. So these observations are being made by Kepler, and the first thing that he tells us about is the law of the orbits, according to which the planets revolve around the sun in an elliptical orbit, where sun is one of the foci, the other foci is unknown. I gave you the equation. I told you what is semi-minor and the semi-major axis, okay? And we have observed that while the planet goes around the sun, at one point it is the farthest, and at the other point it is the closest. Is that fine? Yes? This is the first one. Is there any doubt about it? Is there any doubt about this? Okay, here you can see as well. Let me remove this. See, A and B, they are the intercepts. Now this C, I'm not talking about the C because it is more of a mathematical thing, okay? There is a parameter actually called as the eccentricity, okay? Called as the eccentricity, 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 okay? It is represented by E, and it is equal to C upon A. It is just giving you the idea how far is the sun from the center. Okay, C, the distance from the center divided by the semi-minor, okay, or the major, whatever. If it is on the major, then you have to divide it by A. If the sun was here, then you have to divide it by B. Is that fine? This is called as the eccentricity. Eccentricity means how much shifted is the sun, the foci, from the center. Okay, is that clear? Now here I'll name the what is this? The parameters as well in the second law. Okay, so I'll go to the second law. Should I erase it? Should I change it? Is it clear? First of all, the concept is that the path is not circular; it is elliptical. Planet goes around this sun. Sun is not the center; it is the foci. And as per Surah Yasin, which is in the Quran, Allah says that the sun is not at rest. Okay, the sun is traveling along with the planets. It's like this is the core. The core is traveling, and the planets are going around elliptical paths along with the sun, like this. For us, it always seems to be at rest, but it is not at rest. It is moving. Okay. Okay. So let me go to the second one. Now what? Yeah. Coming to the second law. Coming to the second law. Now the second law, first of all, let me write down the things about the second law. The second law given by the Kepler, the observation that he made, is known as the law of areas. The law of, okay. What is the statement of this law? First of all, as I told you before, the planet at one point during the motion on the elliptical path, it is the farthest, isn't it? Okay. At one point, it is the farthest, isn't it? And at one point, it is the closest to the sun, isn't it? Now these points, either the farthest or the closest, they are called as, both of them together are called as apses. What are they called? Okay, together. But then there are two types of apses, either the farthest or the closest. When it is the farthest, see, when it is the farthest is a point when we call this apses as apapses. Okay, so I'll show that with the help of marks. So remember, it is apoapses for the farthest. Okay, but when the planet is the closest, okay, the point is called as, yes, periapses. Now it has other names as well. One of the names is apogee. And then this is called as the perigee. But remember, this terminology is used for the moon revolving around the earth. When the moon revolves around the earth, when it is at the closest, we say perigee. And when it is at the farthest, we say apogee. But you need to understand, ap is the farthest and peri is the closest. Okay? Fine? Similarly, we have one more terminology. We can call this point, the farthest point, as aphelion. Okay? And this point, the closest point, as perihelion. Is it clear? When the planet is at the farthest, we call this, or the closest, both the points together are called as apses. And then we have two types of apses, and it is for every planet. It is not that it is only for Earth. Every planet. For example, we talk about Mars, we talk about Venus. Any planet, it will be farthest as well as closest. The farthest is called as apoapsis. The closest is called as periapsis. The farthest for moon is called as apogee, and the closest is called as perigee. It can also be called as aphelion, and this can also be called as perihelion. Is that clear? This is the terminology associated, because you need to understand what is happening. Fine? Now comes the second law, the law of the areas. What? The law of the areas, okay? Should I erase this terminology? Okay. Now see, what is the second law as per the Kepler? Very important thing. As per the Kepler, the second law is called as the law of the areas. The law of areas. And as per this law, what he says is, when the planet revolves around the sun, for example, this is the radius vector, isn't it? Isn't it? As per Kepler, if for example, I ask the planet to travel for, say for example, to travel for 5 minutes. So after 5 minutes, it will cover some distance, isn't it? Yes? Say for example, the planet is here. Therefore, this radius has swept some area from this point up to this point, isn't it? And this is the area, right? Yes or no? Yes? So for 5 minutes, let the area it swept be A. I have represented by the orange color, okay? As per Kepler, when the planet is at some other point, for example, now the planet is here. Okay? The planet is here. Now I am again so the radius vector is this, yes? Now I am again asking the planet to travel for how much time? 5 minutes. Okay? Again the same time, I am giving it the same time. And I am seeing how much area will it sweep now. As per Kepler, he was astonished to see the planet reached this point and the area that it swept was this one, isn't it? And would you believe both the areas were same? Both the areas were same. When the here the distance traveled by the planet is only this much, isn't it? Yes? But here you see the distance traveled by the planet is more. possible that in the same time, at one point it is covering less distance, and at other point it is covering more distance? Yes?
Because as it travels closer to the sun, the speed.
Exactly. So that is how he came up with the conclusion that the speed should not be constant. That was your question, right? Why is the speed different? This confirms that speed here should be less and speed here should be more, isn't it? When the speed is more, it will travel more distance, but at the same time the area remains same. At this point the speed should be less, therefore it will travel less, but the area will be equal to the other area. Is that fine? Is it clear? So this is the law of areas. Write it down. This is the definition of the second law. The statement rather. As per the law of areas, the radius vector sweeps equal areas in equal intervals of time. Full stop. Very important thing that you are going to write. This law is in accordance with the law of conservation of angular momentum. This law is in accordance with the law of conservation of angular momentum. Do you know what is angular momentum? Yes? See, the equation for angular momentum is this. L is equal to mass into velocity times the distance. Okay? Now see what is happening. Actually, when the planet is revolving, there is no external torque. Okay? When there is no external torque, the angular momentum of this planet remains conserved. That means, if this is the point A, if you apply the angular momentum equation, so it is mass times the velocity at this point times the distance, okay? Same value will be applied here. It will be mass times the velocity times the distance. Now, as per the concept that the angular momentum is conserved, can I say mass and mass will cancel because it is same at both the points, right? But at this point, the distance is more. So distance is more. At this point, the distance is less. So distance is less. But in order to keep the product equal, how is it possible? Yes, there is only one possibility, that when the planet is here, its speed should be low, and when the planet is here, its speed should be high, isn't it? For example, the product is 10. So that means M1 V1 R1 should be equal to M2 V2 R2 should be equal to 10, isn't it? For an example. Now because mass is same, it will get cancelled. So therefore we can say V1 R1 should be equal to V2 R2. Yes? But we know for the product to be 10, for example, the distance here is 5. But the distance here is 2. So that means this is V1 times 2 and this is V2 times 5. How is it possible that we maintain the product?
Sure.
Yeah, this should be 5 and this should be, right? So the speed here is less and the speed here is that clear? This is the conservation of angular momentum. And as per this concept, he says that the planet, when it is at apoapsis, it slows down, and when it is very close, the speed is very high. So when the planet goes very close to the sun, remember, its speed is high. When the planet is very far away from the sun, its speed is, this is the deduction from the second law, the law of areas. Write it down. What did you write? This is in accordance with the law of conservation of angular momentum. Full stop. Full stop. You can write this. L is equal to mvr. So m1 v1 r1 is equal to m2 v2 r2. Masses are same. You cancel them out, and therefore the velocity here is more. The velocity here is less. The radius here is more, and the radius here is less. Something like this, so that you don't forget what you learned. Okay? Is it clear? Fine. So write a deduction. The conclusion that we can make. Write it down. Thus, as per this law, the speed of the planet around the sun doesn't remain constant. The speed of the planet around the sun doesn't remain constant. Thus, as per this law, the speed of the planet around the sun doesn't remain constant. Full stop. It increases when the planet gets closer to the sun. It increases when the planet gets closer to the sun and decreases when it goes away from the sun. Fine? And decreases when it goes away from it. Increases when it comes closer to the sun and decreases when it goes the speed. Okay? Because we are talking about the magnitude here. Okay? It increases when it goes closer to the sun and decreases when it goes away from the sun. Okay? Full stop. This happens to conserve angular momentum. This happens to conserve what? Angular momentum. Is it clear? Is there any doubt in this? Okay. Now see. Should I erase it? Because I want to show the simulation now. Fine? Now see what is happening. Now see the simulation. Very important, okay? I'll try to move this planet at a, because I want to see, this is the apoapsis, the point which is the farthest, the apoapsis, okay? And then we have the periapsis, which is the closest, okay? And you can name this as perihelion, you can name this as perigee, and here you can name it as apogee, aphelion, or whatever you want. Okay? Is that fine? So these are the 2 points, apoapsis and the periapsis. These are marked on the diagram as well. Now let me play the simulation. Now see what is happening. See what is happening. From this point up to this point. So I have splitted the area around the sun into 3 segments. Okay. And I am giving the same amount of time. How much? 0.62 years. I am asking the planet to travel for how much time? 0.62 years. Okay. Here as well as here. So what is happening? When the planet is here, it covers an area of 2.28 astronomical units square. Astronomical unit is the unit of length, okay? And when you square it, it means it will be the area, fine? So 0.62 years time. Here as well, I gave it the same time. But what I am seeing is when the planet is going around the sun, when the time was fixed, so what happens is the area traveled here is equal to the area traveled here, isn't it? Similarly, see what will happen. See, for the same amount of time, 0.62 again 2.28. No matter how much time you fix, Whatever the area it is going to cover in one segment, same area it will cover in the other segment as well. Is that fine? If I increase the number of segments, see, I now am splitting it into 4 segments. See what is happening? See? Now the time allocated is 0.47 years. Here as well, here as well, here as well. So what is happening? The area covered by the planet in this time, in this segment, is 1.71 astronomical units square. Here as well, in the same amount of time, the area is same. So the area, no matter where the planet is, always remains same if the time period is fixed. So this is the law of areas. Is that fine? And you can notice it here as well from the swept area graph. See, if let's play it again. See, look at this. The period first, second, third and fourth, and see the area that has been covered. Area remains the same. In the first time, you know the time here is 0.47 years. So 0.47 in the first case, in the third case it is the same, in the second case it is the same, in the first case it is again the same. Is it clear? So how is the area same everywhere? That means when you look at the speed, see the speed. Speed is now increasing as the planet is approaching the sun. When it is going away from the sun, speed is decreasing. So this confirms actually angular momentum has to be conserved, and in order to conserve that, the speed of the planet varies. It increases, it decreases, so that the area that it sweeps remains fixed, remains constant. Is that clear? Is there any doubt in this? Fine. This is the second law called as the law of areas. Fine? Okay. You can also use your stopwatch no matter what. If you want to, say for example, do some other things. See, the number of segments have been increased to 6. See what is happening? The area allocated is 0.31 years. Okay? And the area the time that was allocated is 0.31 years. And the area that it sweeps is 1.14 astronomical units, here as well, here as well, here as well, everywhere. No matter where the planet is, no matter what the time is allocated, whatever it is allocated, if it is fixed, the planet will always cover same areas. But at the same time, the distance, see, very important, very important. The distance that the planet covers. Here, see, very important. The distance that the planet is covering here is this much, isn't it? This is the linear displacement, isn't it? But here, see, is it more or less? More. Here, it's again less. Here, it is again less, isn't it? So, the length of the arc is different. Why? Because the speed is different. When the speed of a planet is different, it cannot be the same. That is how area remains fixed. Clear? That is your second law, called as the law of areas. Fine? Now I come to the third law, the last law. Okay? Now this law is called as now this law is called as the law of periods. The law of periods. Now what is this law about? As per this law, see, every planet, if I let a planet go around the sun, it will take some time to complete one cycle, isn't it? That time is called as, yes, time period of revolution, isn't it? Time period of revolution, right? Or in other words, you can call that as 1 year, isn't it? Yes? For Earth, what is the time period? Yes? How much is the time period for Earth?
365 days.
365 days and خلاص؟ لا. And 6 hours. Okay? 365 days and 6 hours. Okay? Now every year these 6 hours are neglected, and then you remember after 4 years we have a year called as the leap year, right? In that the Feb has 29 days. Why? That one day is because after 4 years, 6 hours, 6 hours, 6 hours, and 6 hours will be 24 hours, right? And that will be one single day. That has been given to Feb. Is that fine? And do you, yeah?
Is there a reason that it's in February?
Yeah.
Is there like a specific reason that it was put in February?
Yeah, because Feb has only 28 days, that is why. Otherwise, all the other months were 30 or 31, right? That is why it was given to Feb, because Feb was already short of days. And do you know how do you find whether a year is leap year or not? This is year 2024, right? Was it a leap year? Will 2025 be a leap year? It will repeat after 4 years, right? And for the simple mathematics, you can simply go for this. Whenever the year is divided by 4, divided by 4. If you are able to divide it for 1 hour, for 5 hours, 0 hour, for 6 hour, so 506, it is a simple value, right? Not in fractions, not in decimals. This year is a leap year. Fine. What about 2016? Was it a leap year? If you want to check it, just divide it by 4. Okay? So it is for 1 hour, for 5 hours, 0 hour, for 4 hours. So it is 5 for 4, right? You can divide it properly, so it is a leap year. Was 2011 a leap year? No, it's not possible, because when you divide it by 4, it will be a decimal, right? It was not a leap year. So leap year will be always divisible by 4. Okay? You understand why does Feb have now 29 days? The reason is the actual time period of Earth is 365 days and 6 hours. Now this 6 hours is always neglected. That is the reason after 4 years this forms one complete day, and we have to adjust that, otherwise it will be a problem. And when we adjust that in the month of Feb, we call that year as a leap year. Is that fine? And that is always there. For that you have to check it whether you are able to divide it by 4 or not. Clear? Okay, now see. When the planet is going around this sun, around the star, it has a time period. Every planet has a time period. Mars has a time period. Venus has a time period. Earth has a time period, and the time period of Earth is already known. Okay. So as per Kepler, what he observed was, if you take the average of the distance, now see, the distance here is say x, and the distance here is say y. So the distance is not same, right? But if you want to convert this into a circular orbit, remember, in the calculations, whenever we have to take the orbit, we have to take the shape of Earth, we take it as circular. The reason, our calculations become much easier. Okay? That is why we have taken it as circular since the childhood. Because the calculations get easier. Otherwise, in reality, it is not circular. Okay? Now, for example, we say that the Earth is going around the Sun in a circular orbit. Okay? In that case, it will have some radius, right? Isn't it? So, do you know what Kepler said? He said that the square of the time period of revolution, if you want to square it, that will be directly proportional to the cube of that average distance around the Sun. This is the law. That means more the radius, more will be the time period. Isn't it? Which planet has the largest radius around the Sun? Yes? Pluto. Isn't it? Do you know what is the time period of Pluto? For Pluto, it is 248 years. That means on Earth, 248 years have passed. On Pluto, if there is a child, he is just 1 year old. Because on Pluto, it takes this many years on Earth for Pluto to cover one cycle. But when you talk about Mars, Mars, or you talk about Mercury, let us talk about Mercury. Do you know what is the time period of Mercury? It is 88 days. That means, if I am on Earth 88 days means 3 months, right? Isn't it? Nearly 3 months. So that means on Earth just 3 months have passed, but on Mercury 1 year is already over. So that means in 1 year on Earth, there will be 4 years on Mercury, right? So that means if I am 30 right now, on Mercury I will be 120 years old. So that means I am old.
Will we grow faster or?
La, it's not about the aging of the body. The number there is 120. 120 on that planet will be very less. Understand? And on Pluto, 1 year will be too much. Do you know? Allah subhanahu wa ta'ala says, and at the time after the Qiyamah is there, 1 day will be equal to 50,000 years on Earth. Do you know? How is it possible? The sun has to be distant, isn't it? Just try to understand. Sun will be distant, and due to that, the planet will take a lot of time. 50,000 years. Do you know? There is a hadith in which Prophet Muhammad, all of a sudden there was a voice, and he said there was a stone which was falling in Jahannam, and now it touched the floor. Have you heard about this hadith? No? There is a hadith in which Prophet Muhammad, he's with his Sahaba, and they're talking, and all of a sudden there is a big noise. And then Prophet Muhammad says that actually there was a rock which had fallen from the top of Jahannam, and today, after so much time, it reached the floor of Jahannam. That was the length of Jahannam. Okay, but actually in that cycle, in the heavenly days, it is just 1 day, but on Earth it had taken 50,000 years. Do you understand? So that means the possibility, see, when Pluto is very far, 248 years on Earth, 1 year on Pluto. That is the same thing, isn't the concept same? So after the doomsday, after the judgment day, what will happen? 1 day there will be 50,000 years on Earth. How is it possible? That means that place where Jahannam is has to be very far away from something, from a star, right? Then only the time period will be too much, and therefore 1 day there, here we will have a lot of time. We will have 248, we will have 50,000 years. Do you get it? So that is the concept. Now, the law of the periods can be, just take a picture because I want the space, I want to write something. Write it down. As per the law of periods, the square of the time period of revolution, is directly proportional. The square of the time period of revolution is directly proportional to the cube of the average distance. Do you know why I write average? Because the distance is not same, okay? So I am taking the average, x and y, I am taking the average, okay? Is directly proportional to the cube of the average distance. Is that fine? Clear? So now see the simulations.
Cube of the
What?
Cube of
the average distance. See the simulation. See, I tried various combinations. I tried to plot. So it means if I try to plot a graph between time period and the distance, will the graph be a straight line? If I plot it between time period and simply the distance, it will not start from the origin. See, the graph is not starting from the origin. T by A is 1.22, so it's not 1. Proportionality means if it is in the numerator, it is in the denominator, the ratio will be a constant, okay? Is that fine? So here what you see, when I plot the graph between T square and AQ. See, now the graph, the ratio comes out to be 1, okay, and we are seeing that it starts from the origin. That is how he came up with the combination. He was measuring the time period, he was measuring the distance, and then he came up, what is the possible combination in which I can fit them on the graph? And when he tried to fit the combination, he see, every combination is mentioned. T and AQ. The graph is not straight. T and A square. The graph is again straight, but see, it starts like this. Starts from here. It's not possible that we can have zero distance and there will be still some time period. It's not possible, okay? So this was again not correct. Now the graph was plotted between T and A. The graph isn't again straight. Then he changed the values of T. He plotted T square with A. Again there is a curve. He plotted T square with A square. With A square. The graph is again some curve. But when he plotted T square with A cube, it is a straight and passing through the origin. Therefore, he came up with the conclusion that T square is directly proportional to AQ. Is that fine? This is the third law, the law of the periods. So, as per this law, this is how we come up with the concept that, see, here the planet is at some distance, some average distance, and the time period of this planet is 1.84 years. Now, if I change the planet, if I talk about Mercury, see, the distance of the Mercury is very less, right? The time period will also be less. When I talk about, for example, Jupiter, see, here it is, the Jupiter, and Jupiter has more distance, average distance from the Sun. When the distance is more, time period will be, and I told you for Pluto it is 248 years. For Mercury, which is very close, it is just 88 days. 1 year on Earth is 3 years, 4 years on Mercury. And then if you are 20, you will be 80 years old on Mercury. If you are 20 here, you will not be even 2 months old on Pluto. Understand? Pluto is very far away. 248 years on Earth takes 1 year on Pluto. Is that fine? That is it. Is there any doubt that you would like to ask? Did you understand all the 3 laws? Now do you understand how do the planets revolve around the Sun? So the equation first was, it is an elliptical orbit. Second, Sun is not the center, it is the focus. Third, the speed is not constant. Now fourth, more the distance, more will be the time. Is that fine? Thank you so much.